You get the second chance.
So you were pleased with the theories.
That was the choice.
Okay. Okay. First off, I would like to thank every one of you for coming out today. I will be presenting my master's thesis on enhancing FPGA productivity with a backend similarity matching of digital circuits. So, an overview of today's presentation. I will start off with an introduction and then present some background and implementation details. Then I will present results for the implementation, and then I will conclude this presentation. So first off, FPGAs have been used for a wide variety of applications. However, designing for FPGAs are becoming more and more difficult as the design size grows in both complexity and size. One reason is because majority of the time spent in the design cycle is in the verification and debug stages. So one solution is to try and promote the idea of reusing existing designs. By doing so, the user won't, assuming the existing design works as intended, the user won't have to spend time trying to verify the design, and then a majority of the time can be spent trying to integrate the circuit into the overall design. So the idea of reuse is heavily seen in software in the form of software libraries. However, this is not new in hardware as well. However, the idea of reusing hardware has not gained widespread acceptance. Reasons are because a lot of the IP cores are private to certain companies or organizations. There are performance issues with reusing someone else's design. There are multiple platforms to take into account, and the user would have to familiarize themselves with the different components in the library. However, if all of these were integrated or somehow extracted away from the user in some sort of design environment, then reusing existing designs would be more appealing to the overall user. So an example of the use case is we have a designer, and he's designing some sort of circuit, for example, like an adder or something. And then the idea is that you have a backend that continuously monitors the circuit that the designer is designing and compares it against a database of existing designs. The backend, after the comparison, the backend will suggest similar matches, existing designs that match the current design that the user is currently working on. However, we don't want to focus mainly on finding exact matches, but have some sort of metric that we can say this circuit is this similar to the circuit that you are designing, so the user has more option to choose from. So with that idea, in order to compare two circuits, we need some way of matching, perform some sort of matching between two circuits. There are two main ways of matching circuits. The one is trying to match their structure. The second way is to try and see how they're functionally similar. So for the first one, in order to match it structurally, we have a circuit, and we want to convert it into a graphical representation. So in this case, the logic gates in the circuit are represented as vertices in the graph, and the nets in the circuit are represented as edges.
Question. Your circuit has some fan out. How are you capturing fan out in the graph? So I can see how the graph directly maps to a fan out free circuit, but if you do have fan out, well, graphs gives you edges between two vertices.
Right.
So if the edges are the wires,
Mm-hmm.
how are you capturing wires that connect more than two vertices? Maybe it's clear in your example.
Right. As far as that goes, I think I'll be explaining how I'm getting the graphical representation of the circuit in a later
Okay,
section.
well, as long as you cover it, there are different ways to do it.
Right.
As long as you describe which way you're doing it.
Okay. All right.
Maybe I don't understand the question. So in the graph there's node A that has a fan out of 2, I guess.
Well, it has 2 edges, right? But are those 2 edges really representing the same net?
What do you mean by the same net?
Well, are you distinguishing sources and sinks?
Right. Yeah. So so I guess it's not really clear in this graph because I don't have arrows pointing out, but ideally the graph would be a directed graph. So you would have arrows pointing out from A that points to A1 and X1, which is seen up here where A goes into both X1 and A1.
Okay.
Up there. I will be going into more of how I'm actually getting the, in terms of the implementation part.
So there's a generalization of a graph, a hypergraph that you talked about at the beginning of the thesis that does allow more than 2 nodes per edge. So that just is sometimes a more natural way to capture the circuit.
Okay. Right, so after the graphical representation of the circuit has been extracted, we can then apply a wide range of graph matching algorithms in order to compare the structure of the 2 circuits. However, by comparing the structure of 2 circuits, that doesn't necessarily kind of describe how 2 circuits are functionally. So on the other hand, we would have to compare the function of the 2 circuits. So one example would be, given the 3 circuits shown up here, we can see that all 3 of them are structurally different. However, they are all functionally equivalent. These are 3 different implementations of 2-input XOR gate. So because of that, there are a wide range of methods out there to try and compare the functional equivalence of 2 circuits. However, as for the purpose of this thesis, I'm not going to go over too much about the functional matching. Rather, I'm going to focus more on the structural matching of 2 circuits. So as far as the implementation goes, the overall system, we have a front end and a back end. In the front end, the user has a reference design that he's currently designing. From the reference design, a netlist is generated. Oh, okay. From the netlist, the circuit is converted into a graphical representation, where it is then passed into a matcher. The matcher then compares the reference circuit with a database of possible existing designs, and then from there, it'll output the results to the user. So the front end was designed using a tool called a Zero, which is a graphical hardware design environment. However, the back end was not designed with a Zero in mind. It can be extended to any other design environment as long as a netlist can be generated.
So, Kevin, before you move on, can you show on this design flow where is the design productivity gain that you get?
The productivity gain is pretty much, as the user is designing, the backend will be continuously monitoring the circuit that the user is designing. So
You need a netlist before you can start.
Right. So the idea is to somehow, I guess, have some way of.
Well, the introduction of your thesis states that you can do 3 turnarounds per day. So you can produce, in my understanding, 3 netlists per day. Is that how you mean it?
Well, I meant that around when the user is. The idea is that because designing for FPGAs the turnout isn't as high, but I was assuming that I was going with more of when you're downloading the entire design onto the board. and testing it that way. However, the netlist doesn't require all that place and route step when synthesizing for the board. So only all I'm interested in is just the netlist of the circuit.
But, so, are you making the assumption that the user designs the netlist, or the netlist is a result of the tools?
The netlist is a result of the tools.
In that case, how can your method lead to design productivity improvement?
So as long as the front-end tool, I guess like whenever the user saves his design, then a netlist would be generated, and by doing so, the netlist can be, once the netlist is obtained, then it can be transformed into a graph. From there, it'll be able to be matched against possible circuits in the database. From there, by seeing which circuits match, I'm able to tell the user what possible existing
Okay, but
circuits.
what incentive has the user at this point to decide, oh, I already designed this, let me replace this with what I already designed? Because at that moment, the user has produced the netlist, so the job is done. There's only place and route, which is left.
Right, but as he is designing, maybe during like, if the front end tool, I guess like, saying like the front end tool when you're saving, not necessarily when you're saving when the design is done, but like, you know, when you want to save your work as you progress. So during that saving point, or maybe it has some sort of like auto save where it'll check incrementally the netlist in the background. So once that's done, the circuit is not necessarily the circuit that he's designing, but it may be like he's designing an adder, but that adder is used as a counter or something, or like a larger adder or a multiplier. And so the back-end system would be able to try and pick up those similar matches as he's building his circuit. And so if I can suggest the circuit that he's trying to build.
You're kind of implicitly assuming there's incremental compilation, and it's actually a very advanced environment with chips on top of the system, or words.
Maybe, so we're talking about saving, maybe just as you're typing, you reach the end of the line, then that's the point where you do
But how many designers nowadays write netlist?
No, you're not writing that list.
So, as you finish a line, you need to first produce a netlist.
Well,
Is auto-completion kind of a model of what's going on here?
This can also be extended, kind of like extended to that sense also.
and also please keep in mind the initial front end on this is a graphical entry, so it's definitely more natural. And forgive me, I don't want to. It seems like we're a little stuck there. It's definitely easy, at least more easy to do within a graphical environment. I see your concerns like you're doing behavioral code.
So I'm not questioning whatever your work, right? I'm not questioning that. I'm questioning how you pitch it. How you pitch it is, and even the words that you're using sounds to somebody who's coming from the outside, who hears all these great ideas on FPGA and design productivity. That doesn't match to what you're explaining. That's my point. Just like
Perhaps pitching it as circuit generation, or circuit inference, or something like that. Just emphasizing the circuit aspect of it.
Okay.
Would make that less unexpected.
Good.
Move on.
Okay. Right, so the back end wasn't designed with a zero in mind, and I guess can overall be extended to any most front end tools. So the focus is going to be more on the back end side, where so first, given the circuit a user is designing, as far as a zero goes, a zero will generate a netlist in the format of EDIF, once the EDIF netlist has been generated, torque is used to read in the netlist in order to extract the digital components of the netlist. From there, a graphical representation can then be built. So as far as this probably goes back to your question, where for each node, so each logic component is a vertex which is corresponded by each line. With each line, I have inputs and outputs labeled. So at least for the inputs, I have no, for node 0, I have no inputs to that, but I have 3 outputs that go to both 3, 2, and 1. And then I go through that for each and every logic component in the circuit. So once the graphical representation has been obtained, it is passed to the matcher. For the matcher, 3 different methods were implemented in order to try and compare and see which method best, which is the best method to use to compare a digital circuit against a set of patterns. So the first algorithm is subgraph isomorphism. The idea behind that is, given 2 graphs, G1 and G2, we want to try and find a mapping between the 2 such that G2 is a subgraph of G1. The overall implemented algorithm is based on a popular subgraph isomorphism algorithm called VF2. VF2 is a backtracking, is a depth-first search backtracking algorithm. The details of the algorithm I won't be discussing, but the overall custom implemented algorithm uses it as a basis for it. So an example of how it works is, given 2 circuits here where G2 is the pattern and G1 is the input. First off, the input ports of the circuits are treated differently compared with the other components because they are inputs. They can be matched to any other components in the circuit. So for example, in this case 4, the input port 4 can be matched to the flip-flop 5 in G1 because both components output to similar components. With that in mind, the algorithm starts by trying to find an initial starting point. The initial starting point is determined by trying to find the least common logic gate in both G1 and G2. So in this case, there's only one instance of an inverter and an OR gate in G1 and G2. So either one of them can be used as a starting point. In this case, the inverter is used as a starting point. Once those have been matched, the nodes are marked so that we know that they have been visited. And then we then check the output. So the output of both 6 and 7 in G1, G2 is indicated in yellow. The next step is to check the output again. However, since the second graph has no output, there's no possible match to be made with the flip-flop in G1. So then the inputs are checked. So the inputs of the 2 AND gates are the 2 OR gates. Because they are similar components, they match and we mark them. And then we go on with that. We check the inputs, 0 and 4 match. And then after that, the outputs of 0 and 4, there are 4 possible matches. We can match 3, 3, 3, 1, 1, 3, or 1, 1. Because there are more than one possible path that can be matched, the program then chooses the best possible path to go from by looking at the nodes highlighted in green. So for 3 and 3, it compares the degrees going into the node. So for 3 and 3, both have a degree of 3, and for 1 and 1, both have a degree of 2, because there are no output is connected to that AND gate. Because the degrees are different, it'll try and match 3 and 3 first. If the degrees are the same, it'll check the next component in the path. If those are still the same, then it'll arbitrarily choose one path. But if once it reaches a mismatch, then it'll start backtracking to a known valid state. Once it's at that state, it'll try a different path and go from there. So in this case, because the degrees are different, it matches 3 and 3. Once 3 and 3 are matched, it will keep going until all the nodes are matched or there are no possible matches to be found. In this case, since all the nodes are matched, we see that G2 is a subgraph of G1. However, if we extend both graphs such that G1 has an inverter attached and G2 has a buffer attached, we see that, and if we continue on the path, we see that both nodes are not the same. Because they're not the same, we don't want to rule out the possibility that these two graphs are still similar. So we devised a similarity metric between the two graphs. Similarity metric says that we want to take all the nodes that we found that are a match and divide that by the total size of the possible pattern graph. So in this case, the similarity would be fairly high given most of the graph was already, a mapping was found between the pattern graph and the input graph. As far as the second algorithm goes, because the first algorithm matches when the pattern graph is a subgraph of the first graph, there has to be an exact match that happens. The second one is called maximum common subgraph, or MCS. The idea of MCS is that given two graphs, we want to try and find the largest subgraph that is common to both of the graphs. So in this case, G2 does not have to be a subgraph of G1 in order for a match to be found. So how MCS works is, given two circuits, we want to try and look at all the possible edges between the two that are compatible. So the graph down here represents the vertices of a compatibility graph that is to be built. The vertices of the compatibility graph represents the edges that are compatible between G1 and G2. So if we look at the highlighted nodes, 3 is compatible to 0 in G2, and 11 in G1 is compatible with 0 in G2 because all three edges share the same source and destination nodes. If we go through each and every edge between G1 and G2, we come up with all the vertices in the compatibility graph. Once the compatibility graph has been built, we then have to find a relationship between the nodes. The relationship is determined by the modular product of the two. So how an edge is found is if the edges indicated in G1 and G2 are both not incident on the same vertex. So in this case, 4 and 3 don't have a vertex in common, and 1 and 0 and G2 don't have a vertex in common. Because of that, an edge would exist between the two vertices in the compatibility graph. Another condition for an edge to exist is if both G1 and G2 are incident on a common edge, then an edge in the compatibility graph would exist. However, if one graph has the edges incident on the same vertex but the other one doesn't, then no edge would exist. So if we follow those conditions, the entire compatibility graph, the full compatibility graph is seen here. With the compatibility graph built, finding the largest common subgraph between the two graphs is then trying to find the largest clique within the compatibility graph. And a clique is pretty much a graph where each vertex is connected to every other vertex in the graph. So the highlighted edges represent the largest clique shown here, and the largest clique can be mapped to the edges in G1 as seen here. So we can see that G2 there's two instances of the subgraph G2. However, if the subgraph that is common with both is not the pattern graph, then a similarity metric is also determined to try and see how similar the two circuits are. Basically, the similarity metric means I want to take the size of the largest common subgraph and compare it with the size of the pattern. If the two sizes are roughly the same, then we know that the subgraph occupies most of the subgraph, and we can say that they're fairly similar in structure. The last algorithm implemented is decomposition subgraph isomorphism, or DSI. the idea behind that is the first two algorithms can only compare two graphs at one time. So the idea is that you would take a reference circuit and then go through each circuit in the database and compare them one by one. However, with DSI, the idea is that you take the entire pattern database and you decompose it into a single structure where similar substructures of the circuits of the pattern is represented only once. So that'll lead to a more compact representation of the database. So the overall flow of this is that the pattern database is decomposed by the decomposer as an offline step. So this is not part of the matching. Once the patterns have all been decomposed, it is stored in the decomposition tree where it is used to try and find a match between the reference and the possible patterns in there. So how the decomposer works is, given a circuit in the pattern database, for example, a NAND gate, we want to try and recursively decompose it such that everything is decomposed to a single vertex. So pretty much we partition the pattern into two graphs, and then once we do that, we partition the larger graph until it is a single vertex big. And then we also, as we partition them, we keep track of an edge set. The edge set pretty much tells the relationship between the two partitions. So once we partition them, we keep track of the edges that we remove. So furthermore, this is an incremental process. So any additional pattern that is added into the database, the entire decomposition tree does not have to be redecomposed. So the idea here now is that if we try and add the XOR gate into the decomposition tree, we want to see if there are similar substructures already present in the decomposition tree that we can reuse. So in this case, we can see that a NAND gate exists in the XOR gate right near the bottom. So we use that similar substructure, we map it to the NAND gate here, and then we take the difference between the current circuit and the NAND gate, and we get left with this one right here. A VMAP is kept track of in order to keep track of the mapping that's done between the two circuits, because the vertex labeling is different between the two. And then with the same thing, we keep decomposing the rest of the circuit until it is a single vertex big. If we try and add in another circuit, we see the entire decomposition like so. So with decomposition also, depending on which circuit you decompose first, the order of the circuits in the pattern database, the decomposition tree is not unique. So it'll change depending on the order of circuits that you pass in. So once the decomposition tree has been built, we can, as an offline process, when we're performing a match with a reference circuit, we use the tree to do that. So initially, there are 3 states each node in the decomposition tree can be in. It can initially, all the nodes are labeled unsolved. If there's a mapping that can be made, the node is marked alive, and if no mapping can be made, the node is marked dead. So initially, we look at the vertices, the nodes that contain a single vertex. We then try to find a mapping between that single vertex and the vertices and the components in the circuit. So in this case, there's one OR gate in the circuit, so we map that OR gate as a possible match with that one component. We go through each and every of the single vertices, and we find a one-on-one mapping on the circuit. Once all the mappings of the single vertices have been made, the next step is to try and combine, pretty much build a circuit from the bottom up. So the next step is to look at the nodes whose both child node is marked alive. So the nodes marked in yellow have the 2 child nodes marked alive. As for the first one, since it's a OR gate connected to a inverter, there is no such instance located here. Because there is no mapping to be made, the node is marked dead. As for the other 2, because those structures exist in the circuit, those nodes are combined and are therefore marked alive. We keep going up the tree until all possible mappings have been made. All possible mappings are made when any unsolved nodes, child node, are not both alive. So in this case, the unsolved node, we have either one unsolved or one marked dead. So those cannot be combined anymore. Once we do that, all the nodes that are complete pattern circuits that are marked alive are possible, sub-circuits of the input graph. So seen here, we can see a NAND gate and an XOR gate present in here. However, the NOR gate is not present in the circuit presented. Now, just like the other two, we want to try and find a similarity between two circuits if no complete match has been found. So in this case, as for the NOR gate, we want to try and find a similarity between the NOR gate and the circuit. And the similarity equation here is given. So the idea is that we want to start from the pattern circuit that has not been matched, and we go down the tree. As we go down the tree from the pattern circuit, we look at all the nodes that are alive and then keep track of the number of nodes. However, just because the nodes are alive, we still have to take into account the edges connecting them. So that's why we take into account both the nodes and the missing edges when calculating the similarity, trying to figure out how similar the mismatched circuit is to the reference. So after the matcher finishes matching, comparing the results, or comparing the circuits, it then passes the results out to the output. For the output, we decided to try and go for a kind of graphical interface so that the user can more easily see and compare the similarity of the two circuits between the reference circuit and the circuits in the database. So Unity was used to try and develop that environment. Unity is pretty much a game engine. Unity was used because of the powerful visualization tools that it has as a game engine. And here are 4 different screenshots of displaying the results, where we have a single structure, and from that structure we can easily compare how similar two circuits are based on the size and the depth of the structure. And the user can also access further detailed information by clicking on the possible matches or the circuits that they're interested in. So from there, some of the 3 different matches were tested using several different benchmarks. The first one was a simple benchmark used that was customly made. The circuits in the benchmark consist of adders, counters, and simple gates comprising of less than 10 nodes to a little under 100 nodes, just to kind of see how accurate and how well it performs. The second benchmark was taken from the IWLS benchmark, and those circuits were a lot bigger, ranging from a couple hundred to about 1,000 nodes. So the first thing I'm going to talk about is how accurate the matchers were. So here we see the 3 different matchers. I also added in the match using the VF2 algorithm. VF2 algorithm, I did not implement that. That was implemented using Boost libraries. So that was added in as a form of more of a comparison method to see how well the other 3 perform. First thing off the bat, we can see that VF2 is an exact algorithm in that it only returns exact matches when found. It doesn't really tell you anything about how similar the circuits are to how similar 2 circuits are.
Just clarification. So what is being matched against what?
Okay, yeah. So the database used are listed under circuits. The reference circuit or the input circuit that's used is the 1-bit counter. So for the 1-bit counter, you can see everywhere it matched 100%. It does not have a label here because it is an exact match. Otherwise, it's a pattern if it's a subgraph, if a subgraph was found and it's an input. If pretty much the pattern and the input represents which one is the subgraph is. So the pattern represents that this circuit is the pattern, and then the input represents that the input is the smaller subgraph. It is a smaller graph. So meaning that the input is the circuit here is a supergraph of the input circuit. So with that in mind, all four of them was able to find the exact same circuit with no problem. So the CSI and the MCS algorithm was able to determine the similarity between the two. The similarities were fairly accurate in that it gave high ratings to the adders, whereas the circuit component and the adder component share a similar structure, whereas the AOI kind of the structure is fairly different. So that's why there's a lower similarity with that. As far as the DSI goes, DSI was determined that it was able to find all the subgraphs fairly, all the subgraphs in itself well. However, for graphs that are for supergraphs, it is not able to determine that because one reason is that the other three algorithms match them one by one, so you can easily determine which graph is larger or not and pass that in depending on which one is, pass it into the matcher depending on which one is larger. However, with DSI, because all the patterns are initially decomposed, all you can really search for is the subgraphs and not really the supergraphs of the input. So that's one place where the accuracy is kind of lacking. One thing is that the similarity was given pretty high for the supergraphs. However, as I mentioned, the accuracy is still a bit off in that it gave a high rating to the subgraph AOI as well in this case. As with the larger test bench, the circuits in the database is listed here, and the input circuit used is the S5378 mod. That circuit was modified from the S5378 circuit. Pretty much all that was changed was a gate was taken out from that. So from that, you can see that there was an exact match between there were two matches between them, and with the CSI and the VF2, they were able to find exact matches. However, with DSI, because the modified circuit is smaller, the S5378 circuit would be a supergraph of that circuit, and because it would have trouble determining supergraphs, that's why it didn't really specify an exact match found. However, compared with the other similarity metrics given, it gave a pretty high rating for that specific circuit, so we can still use that as a way of determining if one is a possible supergraph or not. Another reason CSI was able to return similarity metrics for a lot of them. However, for a lot of them as well, you can see that no similarity metrics have been returned. The reason is because of how both of them do matching. So, or how CSI does the matching. CSI does the matching by trying to find an initial starting point to try and start matching. However, if the initial starting point common to both is not a good indication of how similar those two are, meaning the starting point is not a good one, then no possible match, then it'll assume that it failed. It'll say that the two aren't similar in any way or form based on the starting point. So as for the performance goes, the CSI and VF2 are the two subgraph isomorphism matchers. We can see from the graph that there is really no correlation between the execution time and the number of nodes in the database given a input graph. The data set used here was the same as the previous table. So there's no specific correlation. As I mentioned, it finds the starting point, and then from that starting point, it'll try and determine a match. So if it has a small set of starting points, then it won't take long to go through all of them. One reason why VF2 has a spike at that specific location is because of the structure of the circuit. If the circuit has subcomponents that are highly repetitive throughout the structure, you have a large set of starting points that you can go through. Furthermore, if you choose the wrong one, you have many different possible paths that you can go through. So that's one of the reasons why there's a spike there.
This, oh, sorry. Yeah, sorry. In this graph, why are you using a line and not bars or dots? Because this is discrete data that you're plotting, so I don't see the meaning of having, for example, a linear increase in this blue curve. I don't think that linear effect is there in the real output. It's just that you have only fewer data points. Is that correct?
Yes. Yeah, I see what you're saying.
So yeah, so it's a visual distortion which is not there.
Okay. Okay, I understand what you're saying. Okay. And then as for the next algorithm, okay. So one thing I forgot to mention was that in this table, the algorithm MCS was not listed because of performance issues. I will now go over. So in the first graph, you can see that as the input size of the circuit increases from the blue, red, and green, and as the number of nodes in the pattern increases, the time it takes to execute goes up significantly. Especially for the input size of 53, the program was terminated early because it was not able to find it was not able to generate a result compared to like the other three algorithms. So with the second one, we compare how well it performed with the other three, and we can see that it did not. It was nowhere near the other three. Reason is because as the circuit grows, the compatibility, there's going to be more possible nodes in the compatibility graph, and since there are more nodes, pretty much the graph becomes very dense, and the algorithm needed to perform that has to go through many possible matches to try and come up with a possible match for it. So with larger circuits, MCS suffers greatly in that aspect. Now for DSI, two aspects of DSI was compared. The first one was how well it decomposes the pattern graphs as an offline step, and then how well the overall matching algorithm works. So for the decomposition of the database, the database in the last table seen was used. Two different organizations were used where we ordered the circuits from largest to smallest and from smallest to largest, and then pass those in to see how well they perform. And based on the graph, we can see that the larger graph, the order from largest to smallest performed well because of how it decomposes. So when it starts with a larger graph, it'll decompose it into two, but the idea is that it won't put it into the database until it reaches the child node. Because it does not have to compare each node with every single other node in the decomposition tree to find a similar substructure, it goes through really fast. Whereas if we have the larger graph at the very end, the decomposition tree would be fairly large at that point. So we would be comparing a very large graph with a number of possible patterns in the decomposition tree, leading to a higher decomposition time compared with the other one. As for DSI, as the number of patterns increase and the number of the input circuit size increases, the overall time increases as well. This is different from what we saw with CSI and the VF2 algorithm, because as the input circuit size increases, the mapping that needs to be made is much larger. Because it is much larger, as you move up the tree, it has to keep track of the different mappings to be made. So there's a lot more copying of these mappings involved. and because these mappings are larger, there's a lot more numbers to be copied as well. As
So which ones, was it MCS or DSI that really consumed physical memory?
It was DSI because the number of mapping that is, if you have a large circuit size, each step of the tree, it'll have to copy all the possible matches.
I can see how both of them are doing. So I don't want to get into minutiae, but was some of these astronomically long times due to the limited physical memory in your machines? Or were you able to normalize that out?
Well, those were with the larger circuits where I kind of left them out as for now to try and I left those circuits out from the test set. I was still running into a lot of memory issues with those larger ones in the terms of I tried a couple circuits that were on the scale of around maybe 15,000 or so, and I was running out of memory on that. At the same time, the machine I was using only consisted of around 3 gigabytes of memory.
Yeah.
So if I could try and use a different computer.
Well, I just want to make sure once we get those big ramps, they're actually due to the computational load of these, not due to thrashing.
No, yeah, it's.
Are you, you're describing, your assumptions about how things are input. Are you making some assumption about hierarchy, limiting the size of circuits? So would you apply this, your examples are all primitive.
Right.
Circuit, primitive nodes. Are you assuming that, you then build components and then design a circuit of those components and then repeat? Is this probing the time and memory usage is that important, or are you ever requiring that you flatten your whole design and apply these algorithms?
As for now, I'm assuming that a lot of the circuits used are fairly flattened to primitives. So
Can you apply these algorithms to circuits that aren't flattened?
I think it should be able to. There's no problem doing that, except the only thing is that the patterns would have to somehow correlate or use the hierarchical blocks. So if your design used like an adder, then somewhere if you want to try and match like maybe a counter that uses an adder, then you would probably have to have that instead of the patterns flattened, you would have to have the patterns in a hierarchical form as well.
Can your algorithm maybe do this? Can you have a pass where you infer one level of hierarchy and then you collapse those nodes and then apply it again? And could you sort of infer a hierarchy of?
I think it can be extended to do that. Yes. Yeah.
So you're either assuming the hierarchy exists, or you are going to try and infer a hierarchy. Which of those two?
That's a good distinction.
I think
So if hierarchy exists, that's something you maybe want to make use of, because that's
right. I guess
quite powerful.
Trying to infer a hierarchy would be. I guess it would have to be to try and I'm sorry, what was the other one?
Oh,
It was
well,
like
so
trying
you
to-
either, the hierarchy already pre-exists, right? And your algorithm uses that. It doesn't just throw it away as the first step.
Right, so it'll probably just do that because essentially we can just put more patterns into the database that has the hierarchy already existing in there, and then we just.
So you have a database of patterns. Those patterns could be more complicated things,
Mhm.
and patterns could refer to other patterns.
Right, something like that. Okay. And then the overall scalability of the three main algorithms, MCS was left out as well in this one because of the high execution time. But from here we can see as we increase the number of patterns in the database, the decomposition, the DSI algorithm was able to scale fairly nice compared to the other two. The reason why there was a big jump in VF2 was because of that one circuit that that spike in the earlier graph that we saw. Overall, in conclusion, as far as performance goes, DSI would probably be the best bet because of how it represents similar substructures in the pattern only once, so it does not have to go through each and every pattern in the database individually. As far as accuracy goes, DSI, like I mentioned, is not able to figure out if the input graph, if the pattern graph is a supergraph of the input graph exactly. Whereas if algorithms such as MCS or CSI will be able to do that because they do it one by one, so they know which graph is larger. They can pass it into the parameter as a parameter individually as so. And then that concludes my presentation. Thanks. Any questions?
Any further questions? Yes.
Kevin, could you comment, did you spot any false positives in your matching of the graphs that you actually find similarities between two graphs that they are not similar in terms of functionality?
Right. So as far as CSI and MCS goes, these were fairly accurate in their
But here on this list, you are comparing only others, like the circuits that came.
right. But there's I guess I could have made the test more extensive, but there was a AOI gate in there that had a completely different structure, and because of that, we can see smaller similarities between the two. As far as false positives, like I mentioned in the DSI algorithm, where because of, I guess, a similarity metric applied, it gave a fairly high rating even though the structure is fairly different. So the reason is that I guess it placed a lot of emphasis on the type of nodes that matched. However, it didn't place as much emphasis on the interconnects. So I didn't play around much with trying different similarity metrics, but that could be one thing that could be further explored in this.
It would be like weighted matching, right?
Yeah, something like that.
And AOI stands for what?
It's like a, so the AOI gate in this case was implemented as two AND gates with the outputs connected to a 2-input OR gate that's inverted.
You do a nice description of background information. One thing I might have overlooked it, but something not too different than this is used in practice, goes by different names, but formal equivalence checking. Most often applied between RTL and a net list, but can also be applied between two net lists. And the back end is often something like a SAT engine. And so it is, well, I think something to include in your survey.
Okay.
And SAT solvers are very powerful these days. And so I think that is maybe state of the art. You're using more fundamental graph algorithms,
right.
But you should look at what people are doing with equivalence checkers.
Okay.
And,
so that just compares the RTL versus the...
Well, there's two versions, right? RTL versus netlist, but also netlist versus netlist.
Okay, but it compares to see if two netlists are equivalent. Okay, right. So, I did not come across that during my research during the background, but I guess like one aspect that's different from mine was I was more trying to find, I guess, how similar two circuits may be, not necessarily how, if they were functionally equivalent.
Okay.
But yeah.
And just one final, I wrestling with how you describe what you're doing. My takeaway is you're doing, or hoping to do, something like concurrent circuit entry and pattern analysis?
Right,
Does
something
that
like that.
capture it?
Mhm.
Okay.
No more questions?
I'm done.
I got one. So because you're comparing structural net lists, but assuming a higher level entry, is the basic idea that you would have had higher level entries of these reference designs that would have been synthesized with the same tool, and therefore there'd be a structural similarity? Or is it like, because the exact ordering of the gates and the exact structure is very important for you to match it,
Right.
would you need to have like the same synthesis tool or whatever tool you use on both the reference and the original? Or could you just grab net lists off the internet or that you find and hope to structurally match them as well?
I think you can do that. Like it doesn't have to use this same tool to synthesize both the pattern and the reference.
Okay.
As far as in my case, like I could for one of the smaller circuits in the IWLS database, I kind of drew out the circuit and by using the primitive gate. So if I decided to make design another circuit in a Zito and try and generate an EDIF file for that and convert that to the graph, I can compare the two if they have similar structures in that sense also.
But right now, I mean, if you had something like AND OR logic,
Mm-hmm.
and another circuit had like a NAND logic, just because of the way it spits out, that would be a problem right now, right?
Right. Yeah.
Okay.
So that was something I mentioned in like the functional part where like just because they're two have different structures, like the structural matching won't be able to pick it up, but whereas functional matching would. But the other thing would be that one possibility is to try and I guess put try and come up with all the possible combinations of a specific.
Or normalize the circuit to begin with.
Yeah.
Look for these patterns and convert them all to NANDs.
Okay.
That's what she was going to say. Thank you very much, camera and